Hi there, my name's Luke Gorey, and in this Snabb brain dump I'm going to talk about sliding windows, and particularly I'm going to draw a parallel between the sliding window that TCP uses to efficiently send packets in parallel and deal with network latency, and the sliding window that an Intel CPU uses to efficiently execute instructions in parallel and deal with memory latency. I'm going to suggest that these are basically the same thing, and that that's practical if you're a networking person who already understands TCP, because you can use your mental model of the sliding window to bootstrap a quicker understanding of how the CPU operates and more easily optimize your programs. So here we go. I have a little diagram here. On the left hand side I have some TCP packets, and on the right hand side I have some x86 instructions. I've actually chosen these packets and instructions at random, so please don't bother trying to see what they mean. We just need some to look at. And what I'm going to do is first run through how the TCP would send the packets, and then run through how the x86 would execute the instructions and see the similarities. Here we go. So we're a TCP stack. We've got a bunch of packets here that we want to send. We want to send them efficiently. How do we do it? Well, the simplest way that you could kind of imagine sending those packets, I suppose, would be to just do them one at a time. So for example, you take the first packet here, and you send that over the network, and you wait until it gets to the other side, and you wait until an acknowledgement comes back, and then once it's acknowledged, then you can drop it and move on down to the second packet and send that across and wait for the acknowledgement to come back, and so on. But this will be very slow. You're very sensitive to latency there, because for every single packet to go through you need to wait for one round trip. So if the server is a long way away, it will take a very, very long time to make any kind of progress. The other extreme would be to just send every packet at the same time, but that's quite an ask on the network. You're expecting there to be enough capacity to buffer your whole file, which could be gigabytes, so that's not really practical either. So what you actually do in practice is use a sliding window. That means that we pick a good size of window, a good number of packets to send at the same time. I'm going to use 4 here, just because it fits nicely on the screen. And then you say, okay, our window starts at the top above all of the packets, and then it slowly works its way down as we go. So we slide our window down, we say, okay, now we're allowed to send the first packet, now we're also allowed to send the second packet, and the third packet, and the fourth packet. But once we get to that point where the window is full of packets, then we stop sending new packets. So we wouldn't send the 5th, the 6th, the 7th packets here, because they're outside the window. So we have these 4 packets that we can send them all out in parallel. Crazy things can happen to them on the network. They can be reordered, they can be dropped and require retransmission, and so on. And we just do all of those things in whatever way we think is best until we reach the point where the first packet is acknowledged. And once the first packet has been acknowledged as successfully received, then the window can slide further down. And now we still have 4 packets we can send in parallel, but now the first one is out of the way and we can move on to the 5th one. And the window basically just keeps on sliding down as we send more packets and they get acknowledged. We always have a healthy number of packets in the air, in flight at the same time, so we get good throughput and everything is happy. Basically the thing that can happen to throw a spanner in the works here is if the oldest packet in the window would have some kind of a mishap, would get lost in a bad way and require a retransmission timeout or something like that, then our progress is going to be stalled until that packet can get delivered and allow the window to advance. And that's just the way that it is. You need to have a big enough window that you can tolerate a little bit of mishaps and that kind of thing. That's the TCP sliding window. Now, moving on to the x86, it's just the same thing. So here we got a bunch of instructions that the x86 wants to execute, and one way that it could do that, again, would be to just take the first instruction and execute that, and then move on to the next instruction, and then execute that. But see, in the second instruction, for example, this one is accessing memory, and that could actually take a while. So one instruction that just moves things from a register to another register might only take 1 cycle, but an instruction that needs to get something from memory could take a really long time. It might take 100 cycles or 200 cycles or something like that. So you wouldn't want to just execute one instruction and then sit around twiddling your thumbs until that is fully executed before starting on the next one. So what the CPU does is exactly the same thing. It makes a sliding window. That's our nice sliding window. And it says, okay, so I'm going to going to start executing this instruction, and without waiting for that to complete, I'm also going to execute this instruction and this instruction and this instruction. So I've got these 4 instructions that I'm executing all at the same time, and the CPU is going to take whatever liberties it wants internally to schedule the various bits of these instructions, figure out what is the most efficient way to execute them. So if one instruction is waiting on a memory access, it can put that off to one side while it does the work of the other ones. And then when the first instruction here has completed, we say that it has retired, and that allows the window to advance. Then the window can slide down and we can start working on the 5th instruction, and this continues down. And that's how we execute our programs, with the sliding window saying which instructions can be executed together. This is called out of order execution and instruction level parallelism. It's a practical thing, and it masks the latency from the memory subsystem in exactly the same way that TCP's sliding window masks the latency from the network. And again, you can have mishaps along the way. So if the window is sliding down all very nicely, and then for some reason you have an instruction that takes a long time to complete, for example, it's really stalled on a really slow memory access or something like that, then you do get stuck, and your execution suffers. And that's why people are concerned about things like cache misses. They know that if there's one instruction that's going to take a really long time to execute, then okay, you can execute a few instructions ahead, but at some point you're going to stall, and nothing's going to happen in the processor until it's able to retire that earlier instruction. And that's a big part of what optimization is about these days. It is trying to make sure that the sliding window can advance at a decent rate, which means trying to avoid having something that makes it stall. So there you go. Sliding windows, they're handy practical things, and if you're a networking person and you already know about the TCP sliding window, then I hope that this helps you to have a little bit of a better mental model of how the CPU works in the same way. And in future brain dumps, we can look at some other related topics, like how branch prediction ties into this, all of that kind of thing. Topic for another time. Thank you for watching.